Hello students, welcome back to my YouTube channel PD Tutorial, and today in this video I am going to prove Stoke's theorem, and I have also uploaded the Green's theorem statement and proof. You may check the link in the description box. Go and check it out. Let's start the proof. Let's start with the statement first. If f vector is any continuously differentiable vector point function and S is a surface bounded by a curve capital C, then line integral of f vector dr vector equals to surface integral of curl of f vector, unit vector and ds. Let's understand the statement first. We are assuming there is a surface S. Let us consider this is a surface S. Okay. And we are considering any vector point function f. Okay. We are considering, let's draw it here. We are considering a surface S and this surface is bounded by the curve C, and we are considering a vector f which is continuously differentiable vector point function. Then we have to prove the line integral is equals to surface integral of this, where the unit normal vector n at any point of S is drawn in the direction in which a right hand screw would move when rotated in the sense of description of C. What is the meaning of this line? So we are going to take the vector, unit vector n in the direction we apply a right hand screw rule. I hope you have studied that right hand screw rule in the physics in class 10, I guess. Okay. So if our curve is rotating anti-clockwise, this n vector thumb comes outside. So this unit vector comes outside of this curve. If curve is rotating clockwise, then this vector n is coming inside the curve. Okay. So that is the meaning of that right hand screw rule. So let's start the proof without wasting any time. Proof. Let capital S be a surface which is such that its projection on xy, yz and zx planes are regions bounded by simple closed curves, and suppose that the equation of surface can be written as z is equals to f of xy, x is equals to g yz, or y is equals to h xz, where f, g and h are single valued continuous function. So what I have written, we have let a capital S be a surface, and if we have taken any projection of the surface in xy plane or yz plane, zx plane respectively, this surface is bounded by or region bounded by a simple closed curve, like we name that curve is capital C. So the equation of surface will be z is equals to f of xy. So if we take the curve surface parallel to z axis, then this projection is on xy plane. Okay. So the equation of this surface will be in the terms of x and y. Likewise, if we project into yz plane, then x is equals to g of yz, y is equals to h of xz, and f, g, h are single valued continuous function. Now we are going to present this point vector capital F as f1 I cap, f2 j cap, f3 k cap. Any vector point function can be represented in this way. Okay. Now we are going to represent r vector x I cap, y j cap, z k cap. Okay. Now we are going to find dr vector. Then this is dx I cap, dy j cap, dz k cap. Okay. Now the required result can be written as, what we have to find, line integral of f vector dr vector is equals to surface integral of curl of f vector n cap ds. So we are going to put the value of f and dr from this equation. We get f vector f1 I cap, f2 j cap, f3 k cap, dr dx I cap, dy j cap, dz k cap is equals to, and we know that curl of f is equals to del into f vector. Okay, so this can be written as surface integral del into f vector. F vector is equals to this, f1 I cap, f2 j cap, f3 k cap, and dot ds. Now we are going to solve this equation by taking the dot product of each term. F1 I cap dot product of dx I cap dot I cap 1, then f1 dx. Now we multiply f1 I cap dot dy j cap, then I dot j is equals to 0, I dot k is equals to 0. Then these two terms get vanished. So I am going to write it directly. This term left and this is same, j cap, f3 k cap, unit vector and ds. So we are going to prove this. So firstly we are going to find the surface integral as del cross f1 I cap, and similarly we show del cross f2 j cap and del cross f3 k cap, and simply we get added all the equation and we find this is equals to this line integral. Okay, let's start. Let us consider surface integral as del cross f1 I cap n cap ds. So if we see, we can write del into f1 I cap. If you can see, we can write del cross f1 I cap is equals to del. What is del? Del is I cap del upon del x partial derivative, j cap del upon del y, k cap del upon del z, and f1 I cap. Okay, now multiply it. Oh sorry, we are going to take the cross product, so there is cross product between them. Okay, then I cross I 0, I cross I is 0, then j cross I is minus k del f1 upon del y, and k cross I j del f1 upon del z. So we can write, we are going to put this value here, surface integral as del f1 I cap n cap ds is equals to surface integral s minus del f1 del y k cap plus del f1 del z j cap n cap ds. Multiply this n cap with both sides. Surface integral s minus del f f1 del y k cap n cap plus del f1 del z j cap n cap ds. Now give it equation number. Give it equation number 2, and we have to prove this equation, so give it equation 1. Now let capital P be a point on surface capital S and ds be the elementary area enclosing P. Let n cap be the unit vector along the normal to ds at P. So what is the meaning? We are going to let P be any point on surface S and ds be the elementary area enclosing that point P, and n be the unit vector along the normal to ds at P. I have shown this in figure. We are considering any point P in the surface S, okay, and we enclose this point P with this area which is elementary area ds, okay, and n cap is any unit normal vector. Normal means perpendicular to that surface, perpendicular to that surface. So n cap is perpendicular to ds. Then dx equal to dx dy upon n cap dot k cap. Give it equation 3, where dx dy is the projection, dx dy is the projection of ds on the xy plane. Let capital R be the region, R be the orthogonal projection of capital S on xy plane, and let C1 be its boundary choosing z is equals to fxy as the equation of surface capital S. Dx dy is a projection of ds on xy plane. As you see in the figure, this elementary area ds, the projection of this area is here in the xy plane. So this is dx into dy, area of any plane, and R be the orthogonal projection of S on xy plane, and C be its boundary. And this is the surface and this is the projection of that surface S, which is named as R in xy plane, and we named that curve is C1. Okay, this region R is enclosed by the curve C1. And of course this region, the equation of the surface is z is equals to fxy because it lies in the xy plane. Now the position vector of point P can be written as, I know this video will be lengthy, but I have tried my best to make you understand in a very short time. R vector is equals to, we have written earlier also, k cap, and if you can see, this R vector is also written as xi cap, yj cap, and z is a function of fxy. So in this place we are going to write fxy k cap. Now if we find del R vector upon del y, then we will get del x upon del y, and we are going to operate x as a constant here. So this term get vanished, because if we find a partial derivative of any constant, it becomes 0. Then del y upon del y j cap, and f is a function of x and y both, so it also get differentiated by with respect to y k cap. This will become j k cap del f upon del y k cap. Since del r vector upon del y is a tangent vector at P, therefore del r upon del y is perpendicular to n cap. So we are considering del r vector upon del y is a tangent vector at point P. So if any vector is tangent to any vector P, then the unit normal vector for point P is n cap, which is perpendicular to this tangent vector. So n cap dot del r vector upon del y is equals to 0. Okay, because both are perpendicular to each other, so dot product becomes 0. We are going to put the value of this term from here to here. So n cap j cap del f upon del y k cap is equals to 0. So n cap dot j cap plus del f upon del y n cap dot k cap is equals to 0. So n cap dot j cap is equals to minus del f upon del y n cap dot k cap. So we find the value of n cap and j cap. So we are going to put this in equation 2. Putting 4 in 2, we get surface integral as del cross f1 I cap and ds equals to surface integral as minus del f1 del y n cap dot k cap minus del f1 del z. So this is the equation 2. So we are going to put the value here minus del f1 upon del z, z dot n is equals to what? This minus del f upon del y n dot k ds. We know that this f xy, this f is nothing but f of xy and this is equals to z. So we can simply write it z also, del z upon del y. Okay. So take minus common, surface integral minus common, this will become del f1 del y, taking n cap and k cap common outside, this will become del f1 del z upon del y n cap k cap ds. Now on capital surface S, we are going to consider f1 function f1 xyz. This is the function of xyz. This can be also written as xy. In place of z we can write fxy. I already make you understand. So we can simply say, just say capital F xy, just say. Now this del f upon del y is equals to del f1 del x del y. If we find the partial derivative of this capital F with respect to y, we get del f1 upon del x del y. Okay, del f1 del y upon del y, del f1 del z upon del y. Again we are going to use x as a constant. This get cancelled, it becomes 1, and z is also the function of x and y because z is equals to fxy. So we find a partial derivative of this. So this will become del f upon del y is equals to del f1 del y plus del f1 del z del y. Give it equation 6. Use this equation using 6 in equation 5 Equation 5 becomes, oh, we forgot to give that equation, no? So we forgot to give that the equation number. This is equation number 5. So we are going to put this 6 in 5. We are going to put the del f upon del y. In place of del f1, this term. We get surface integral s del f1 I cap n cap ds surface integral s minus del f upon del y n cap k cap ds. So this will become surface integral minus del f del y, and if we were able to found n cap dot k cap ds is equals to dx dy. From here n cap dot k cap into ds is equals to dx dy from equation 3. From 3. Now by Green's theorem, in plane region capital R we have, so we are going to use the Green's theorem. So if you have not seen my video of Green's theorem, please check the link in the description box. You may check it out, and let's see how we are going to apply. So the Green's theorem is line integral of curve C psi dx phi dy is equals to surface integral over R del phi upon del x minus del psi upon del y dx dy. So we are going to use this Green's theorem. We are going to write line integral over curve C1. So this is the curve C1. Okay, C1 psi dx, sorry, we are using the function capital F dx 0 dy is equals to surface integral R del 0 upon del x minus del f upon del y dx dy. By using the Green's theorem, I have written this line. Give it equation 8. It will become surface integral R minus del f upon del y dx dy. This is equation 8. Now C1 f dx. Now we are going to put this 8 in 7. Put 8 in 7, we get surface integral s del cross f1 I cap and dot ds is equals to line integral over curves C1 capital F dx. From 7, give it equation 9. Okay, since at each point xy of C1 the value of capital F is the same as the value of capital F1 at each point x, y, z of capital C, and since the dx is same for both curves, we must have C1 f dx is equals to line integral over C f1 ds. Give it equation 10. So what is the meaning? So if we take any point xy at curve C1, so if we take any point xy in curve C1, the value of the function f1 is same as the value of function f at xyz, and the value of dx dy is equals to same as ds. So I have written this simply that if we take any point xy at C1, the value of capital F is same as the value of f1 at each point xyz of curve C, and dx is same for both curves. We must have f of ds f1 dx. So this both line integral is same because the value of f and f1 is same for both the curve. and this curve will be same because both are the projection of each other. So from 9 and 10 we have, so from 9 and 10 we are going to use it, and we will find that surface integral as del cross f1 I cap n cap ds is equals to, we are going to write line integral over c capital F1 dx. Okay, give it equation 11. Likewise we are going to write line surface integral as del cross f2 j cap n dot ds is equals to line integral over c f2 dy, equation 12, and surface integral del cross f3 k cap n cap ds is equals to line integral over c f3 dz, give it equation 13. Now adding equation 11, 12 and 13, we get surface integral as del cross f1 I cap f2 j cap f3 k cap and unit vector n ds is equals to line integral f1 dx f2 dy f3 dz. So this is the proof of Stokes theorem. We proved that curl of f vector n cap ds is equals to line vector f vector dr vector. We modify this equation into this, so we have to simply prove this line. Okay, so we found the proof of Stokes theorem. I hope you like the video. The video will be lengthy, but I tried my best to make you understand in a very short period. And if you like this video, please hit the like button, subscribe my channel, and don't forget to press the bell icon for further notification. Thanks for watching this video.